What would happen if we detonated an extremely powerful nuclear weapon on the moon? Could it blast the moon's orbit toward Earth, causing massive tsunamis and catastrophic disasters? Could the shattered moon shower Earth with deadly meteorites? Since the Cold War, the moon has been the primary target for space exploration. For more military bases. So the U.S. Air Force commissioned a critical study to understand the effects of nuclear explosions on the lunar surface. But mere citations would be boring. So let's conduct a crucial scientific experiment using a 100 megaton hydrogen bomb. This device will be twice as powerful as the strongest bomb ever detonated. We'll also enlist a few curious astronauts as observers. Let's press the detonator and slow it down. In the first few milliseconds, from the outside, nothing appears to happen. Yet internally, the high explosives have already sent shockwaves through the radioactive metal, compressing it to the critical point where nuclear fusion chain reactions begin. The plasma generated in this first stage, reaching temperatures of 100 million degrees, triggers the second stage, atomic nuclei fusing together like in a stellar core. In this instant, our device encompasses one of the hottest places in the universe. Now, a mere 10 microseconds later, the entire universe finally registers that something has occurred. The bomb rapidly implodes, and a planet scorched by a nuclear inferno is born. So far, so good. But everything that unfolds from here on out will be vastly different from what we know on Earth. For one crucial reason, the moon has no atmosphere. As this fireball releases flashes of X-rays and scorching photons, a silent heat wave surges outward in all directions. On Earth, this heat wave would incinerate everything within a 50-kilometer radius. But on the moon, without an oxygen-rich atmosphere, there is no combustion and nothing to burn. The moon's friable regolith consists of silicate rocks and metals. These metals, pounded into dust by countless meteorites over eons, are mixed with trace amounts of water. As the explosion generates intense heat, the X-rays emitted by the fireball vaporize a layer of the moon's thin surface rock. The unfortunate dust trapped inside the fireball is melted into glass. Any astronaut watching the spectacle within 50 kilometers would be fried crispy by the furious flames. Now, we witness the most significant difference compared to an Earth explosion. Earth's atmosphere resists the enormous plasma bubble. Atmospheric pressure violently and forcefully prevents the explosion from expanding. But this is no good news. As the fireball violently rebounds against the atmosphere, it generates the most destructive aspect of a nuclear blast on Earth, the shockwave. The compressed air around the explosion surges outward at supersonic speeds, shattering buildings while the roaring blast ruptures bodily organs. But on the moon, no shockwave occurs. Without an atmosphere, nothing restrains the explosion's expansion. On the moon, unhindered by air or sound production, the fireball grows in an eerily silent manner. Witnessing it from a safe distance would be astonishing. Unfortunately for a lunar nuclear blast, there is virtually no such thing as a safe viewing distance. Safe viewing distance for a lunar nuclear blast. Without an atmosphere to dampen the lethal ionizing radiation capable of disrupting DNA, anyone seeking a prime viewing spot would be exposed to lethal doses of radiation. And of course, the real show is just beginning. As the explosion strikes the moon like a giant hammer, roughly 1/10 of its energy is converted into seismic waves, generating powerful moonquakes. The moon is vastly smaller than Earth, so astronauts would feel an unignorable violent shaking wherever they stood, comparable to a magnitude 7 earthquake. Such seismic activity would severely damage our lunar infrastructure, or even level it entirely. Those sheltered on the far side of the moon would remain unaware that this all stemmed from an explosion. The sensation of the tremor would resemble an impact from an asteroid the size of the Great Pyramid of Giza. But that is not all. Soil would spatter outward from the blast site, like ripples from a stone tossed into water. As the explosion propelled the surface, it could excavate up to 100 million cubic meters of dust and rock, forming a kilometer-wide crater. With bedrock shattered into rubble, debris would shoot skyward in all directions. Similarly, without atmospheric interference, this debris would surge outward unimpeded. Many scattered fragments would never return to the moon, shooting away its